Welcome to our discussion on optimization problems. Now, there's really no difference with optimization problems in calculus than there are when you deal with optimization problems in pre-calc or college algebra. The only difference is we can now tackle optimization problems that might require some trickier math, i.e. usually requiring a derivative. But the idea is still the same, the general technique is still the same. You still want to read the problem all the way through and understand the problem, right? Step one is to just get an overall feeling for what the problem is asking you. You're looking for specific things, right? What are you given? And then what are you looking for? Then you go back and you pull out all the important information. You go and reread it. And you definitely want to draw a diagram. That's a biggie. You always want to draw a picture if you can. Then you start introducing notation. That's a fancy way of saying give some things some letters. Title things X and Y and A and B, or H for height and T for time, or it doesn't matter what you call them, but you're going to have to start introducing some letters. And then all of this stuff down here, just really the bottom line is you need to find the equations, right? In all of these problems, you're minimizing something, you're maximizing something, you're finding something. That means that you have a given quantity and you have an unknown quantity, and you have to somehow solve for that unknown quantity, and the only way to do that is to come up with an equation that equates the unknown quantity to the stuff you already know, right? So it's all about coming up with those equations. And that's what I like to do, is just generalize it. Don't get bogged down in all the details of 4 through 6. You're really just going to find some equations. Now, in the cases of these optimization problems, the process is going to require taking derivatives because we're finding minimums and maximums, but we don't really want to try and think of this as a completely new set of steps. It's not. It's still solving a word problem, right? And the last step is still to find those equations and then solve those equations. It's just now the tools we're going to use to solve those equations are going to involve derivatives. All right, let's look at a simple example. So a farmer has 2,400 feet of fencing, wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So we've read it all the way through. We've come up with the idea. Right? We see the general theme. We've got fencing. So we have, right, that's how much fence we have. What are the dimensions of the field that has the largest area? That's what we're looking for. The next thing we'd want to do is draw a picture, start labeling things, right? Well, if we did some investigation, we could see that if we had different shaped rectangles, we're going to get vastly different sizes of areas. So it obviously does relate area and shape, right? We can get a different area based on the shape of our rectangle. So it's all about finding that optimum shape. So we're going to draw ourselves just a generic picture of our rectangle. And because we don't need fencing along the river, we only have 3 sides. And since it's a rectangle, we know the 2 vertical sides are the same, so we call those X's and the other one's Y. Heck, if you wanted to, you call them length and width. It doesn't really matter, right? It's just you drew a picture, you labeled your quantities, and now you're going to start finding those equations. Well, the first equation we have is the one we're trying to solve, and that's always a great place to start. We want to maximize area, so you better come up with an equation for area. And since it's a rectangle, length times width. Right? Now, maybe it's a good idea to come up with an equation for what we know. And what we know is that we have a total, right, a total length of fencing of 2,400 feet. Well, according to our picture, our total length of fencing, right, is this measurement, and that measurement, or X plus Y plus X, or 2x plus y, and that equals 2,400. And the reason why we did that is because we looked at our first function here, our first equation of area equals x times y, and we know that we're going to have to maximize that, which means we're going to have to kind of solve for something, and we can't solve for two variables in one equation. It'd be much easier if it's all in terms of one variable. So when we come up with this equation, we can do a simple substitution, right? Solve for y, plug it in, and now we get a new equation all in terms of x. And that's something we can work with. Well, if we were to graph that, right, what kind of function is that? When you have the x squared and the x term, hopefully you can recognize that's a parabola, and the leading coefficient is a -2, so it's a parabola opening down. Maybe it looks something like that. Maybe it looks something like that. Heck, maybe it even looks something like this. But regardless, it's going to have a maximum, right? And that maximum is going to occur where the slope of the tangent line equals 0. Now you may remember from an old pre-calc or college algebra class that that maximum is also the vertex, which means you just need to find the axis of symmetry, and that gives you your vertex. And you might remember that the x part of your vertex is minus b over 2a, and then y is just plugging that back into the function, right? Doing the f of minus b over 2a. And that's how we found the vertex when we were in college algebra, before we knew how to take a derivative. And if we had to do it as minus b over 2a, well, in this case, b equals 2400 and a equals -2, right? Because this is really written as y equals -2x squared plus 2400x plus 0, right? And that would be our c in the ax squared plus bx plus c thing. So minus b over 2a is just simply going to be -2400 all over -4, right? 2 times -2. So we're going to get 600 equals x. So if you go back up to your picture, this is going to equal 600. This is going to equal 600. And if we know 2400 equals 2x plus y, then 1200 has to equal the y, right, the leftover. And there's the dimensions of our rectangle. And we didn't even have to do any calculus whatsoever. But we can also get to that by doing calculus, realizing that we're maximizing this function, which means we're looking for that critical value, which means we're looking for the slope of the tangent line to be 0, which means we're taking the derivative, setting it equal to 0, and solving, and getting the exact same answer. Now this is technically a closed system, right? Because we have a finite amount of fencing we can work with. So x being the length of the vertical fence, has to be somewhere between 0 and 1200, because if it was 1200, you'd have a 1200 length up and a 1200 length back down, and you'd be all out of fence, right? So technically with an optimization problem, you're supposed to check your endpoints as well. But it's pretty obvious that the endpoints won't work, because if you plug in 0, you get an area of 0, and if you plug in 1200, you're also going to get an area of 0. Now if we want to figure out what that area actually is, then we can go back and we can plug 600 into the area formula, or realize that, you know, we've got 600 times 1200, multiply those together, and there's your 720,000. Alright, the first derivative test for absolute extreme values. This is just a reminder, we've already seen this, but suppose that c is a critical number of some continuous function defined on some interval. If the derivative of the function is greater than 0 for all x is less than c, and less than 0 for all x is greater than c, then it's the absolute maximum, and then you see the other thing is the opposite. Oh, blah, 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 right? Lots and lots of words. We know this. We don't need to put words to it. We understand what it means. If the first derivative is greater than all x less than c, then that means, so here we are at some point c, If the derivative is greater than 0, that means the function is increasing on this interval until we get to wherever c is. And then the function, right, the derivative is less than 0, which means the function is decreasing. So of course, this is a max. Right? This first derivative test for absolute extreme values is just basically talking about the first derivative test in general. Okay, so we're just rehashing what we already knew. How about an application to business and econ? So we know that if the cost function is the cost of producing X units of a certain product, then the marginal cost is the rate of change of your cost function with respect to X, with respect to a change in X. Usually it's an increase of 1 unit because you can't increase a tenth of a unit, but it's still kind of that same idea as how fast is the cost function changing with respect to a small change in X. What does that sound like? Hey, that sounds like a derivative, and therefore we get the marginal cost function is in fact the derivative of the cost function. Same thing with the function px being the price per unit that the company can charge if it sells X units. Then p is called the demand function or the price function, and we would expect it to be a decreasing function of X just because of the way price and how many units it sells are related. So if X units are sold and the price per unit is this function P of X, then the revenue you get is price times units sold, or X times P of X, and that ends up being your revenue function. And just like the cost function, we can calculate marginal revenue by taking the derivative of the revenue. And then of course profit is just revenue minus cost, which gives us a whole new function that we can again take a derivative of and get the marginal profit function. So we're just describing these marginal functions if you haven't already seen them in an econ class. So with that in mind, let's look at this example. So a certain store has been selling 200 Blu-ray disc players a week at a price of $350 each. They go out and do some market survey research, and they figure out that for each $10 rebate that they offer to their buyers, the number of units they will sell will increase by 20 in that week. They'll sell 20 more units a week if they cut the price by $10. So based on that, we can find the demand function, the revenue function, we can find the profit function, all these things, and then we can figure out how large a rebate should the store offer in order to maximize its revenues, right? How much should it give off? Should it be 10, 20, 30? How much of a rebate should they give in order to maximize their profits? Because remember, the more money they take off the price, the more units they sell, but they're also making less money per unit. So there is, kind of they can't just take all the money off to sell more units. There has to be a kind of an equilibrium point in there. All right, we've identified the problem. We can't really draw a picture here, but we can start labeling some things and coming up with our equations. So we know that if X is going to be the number of Blu-ray players sold in a week, then the weekly increase in sales is going to be X minus 200. Now where did that come from? Well, that came from the fact that 200 is where we started at. Now you could have let X be the increase in Blu-ray sales, and then everything would change, all of our equations would be different. It just turns out that it's easier, mathematically speaking, to always let X be a number of things rather than a change in a number of things. It just gets confusing with a derivative being a change of a change type of thing. So it's better to let X be the number of things. So if you sold 250 Blu-ray disc players, right? 250. X would be 250. That would be 50 more, right? Because you started at 200. So that's why the weekly increase is going to be however many you sell minus the original 200 starting point. And for each increase of 20 units sold, the price goes down by 10. So every time this X minus 20 equals a multiple, X minus 200, every time X minus 200, every time this, which is our increase, right? Every time that increase equals some multiple of 20, the price goes down by that same multiple of $10. Or more specifically, if we want to relate it back to 1 unit, for each additional unit sold, the decrease in price will be 1/20th times 10. And therefore our demand function ends up being 350 minus 10/20 times x minus 200, blah, 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 right? Okay, now you might be thinking, all right, where the heck did all of that come from? Okay, well, let's walk through this kind of slowly. Recall that the increase, right, is x minus 200. That's the increase in units sold. And we're just going to say that's going to equal some number A. Okay, we don't know what it is. Could be 10, could be 20, could be 15, could be 7, could be 3,000. We don't know. A is just the increase in the units sold. Now, according to the market research, every time that increase, or it kind of comes the other way, every time the price goes down by 10, this increase ends up going up by 20. So we can let this number A be the same thing as just 20 times some other number K. Right? We're just calling it two different things, Bob and Robert. Now we know that our new price is going to equal the original price minus $10 for every K, right? So for instance, if we sold 40 more units, then A would be 40, K would be 2, right? That would be 2 increases of 20, which means the price has to go down by 2 tens, because it said every time it goes down by $10, the demand goes up, or you sell 20 more. So you see how this relationship works here? Well, now solve for K. In this case here, K equals A over 20. So this new price is going to equal the original price minus 10 A over 20, and this thing here, right, is just minus 1/2 A. Well, A is just this piece, right? So it really just equals the original price minus 1/2 times x minus 200. See, that's where this came from here. This is really 1/2 x minus 200. And then you just do the math, distribute that 1/2, and half of 200 is 100, right? And you get 350 minus a minus or plus, and that's where you get 450 minus 1/2 x. Okay, so it's a long way to get there, but this ends up being your new price function. Remember, this is a price function. This is how much you price them out at, right? They started at $350. Now they're going to be $450 minus 1/2 of x, where x, right, is the total quantity sold. X is not the increase. Remember, we defined it as the total quantity sold. And that's a good thing, because then it makes it a lot easier to do the revenue function, because the revenue function is number of things sold times this price function. So if x was defined as an increase, right, then the increase in number of things sold, we could no longer just multiply by x. We'd have to figure out what x is in terms of the actual number of things sold. It becomes a big pain in the butt, right? So like I said before, it's much easier if you always define x as number of units, because it's what you're going to need right here when you want to figure out the revenue function, which is number of units times the price. So you just take your price function, multiply it by x, and then there is our revenue function. Now, if we take the derivative of that revenue function, we can see quite easily that it's just going to be that. And then if we set that equal to 0, we get 450. Now we know this is an absolute maximum by the first derivative test, or simply by knowing what this function looks like. Right? If we graph that function, we know it's a quadratic facing down because of the -2. So any critical value we find is going to be a max. And so x equals 450 is our max, which means, remember, that's the number of units sold. Okay? But the question was, what's the corresponding price? So you want to plug that into our price function, and we get 450 minus 1/2 of 450, or 225. And the rebate is 350 minus that 225, which means the price is 125. So in order to maximize the revenue, the store should offer a rebate of 125, right? That's how you bring it down from 350 to that optimal price of 225. So in order to sell them at 225, we need to give the consumers a rebate of $125, and then that will maximize our profits. And we could even figure out what those profits were, or at least our revenue. We don't know what the profit is because we weren't told how much they have to pay for these Blu-ray disc players, but we can figure out what their revenue would be by plugging that into the revenue function, right, of the 450x minus 1/2 x squared. We know that our revenue is the 450x minus 1/2 x squared. We know that if we give them a rebate of 125, the price ends up being 225, and then according to that, x, right, gets maximized and becomes 450. Plug 450 into this function, and that'll give you the maximum revenue you'll make off of your players. Okay, so that's a business example. Let's do one last example. Let's consider the following problem. You have a box with an open top, and it's to be constructed from a square piece of cardboard that's 3 feet wide. And you're going to construct it by cutting out a square from each of the 4 corners and then bending up the sides, and they want you to find the largest volume that such a box can have. This is a typical calculus problem. You'll see these all over the place. We've read it through, we kind of got an idea of what's going on. We have to build a box, we've got a piece of cardboard, we've got to cut some stuff out of it, right? So the next thing we should really do is draw a picture. So here's my picture. Here's the corner that we're going to cut. Each of these we'll just say is a x by x, right? These are all going to be x by x. And when we fold it up, can you see now that if dotted line, dotted line, dotted line, if you fold those 4 tabs up, do you see how it'll create a box that looks something like this? Where this is going to be a height of x, right? This is a height of x, and then this length here and this length there are the same. Right? Can you see how that's a square? And if the whole thing here is 3 feet, then isn't this distance from here to here going to be 3 minus 2x? Now we could have done this in steps, and we could have just called it a y. And then we could have figured out that y plus 2x has to equal 3, correct? Because here's y, and then here's an x, and there's another x. But you can also just kind of draw your picture and go from there and figure out what the leftover. But in either case, right, y ends up being 3 minus 2x. So this is a 3 minus 2x, 3 minus 2x. There's the picture of my box, my open-topped box that I'm creating out of this cardboard. Now if we're trying to find the largest volume, then that means we have to have an equation for volume. and volume is length times width times height, or 3 minus 2x squared times x, right? This one times that one. That's going to be our volume, and we want to maximize that. So if we want to maximize it, we're going to have to take derivatives, right? Set them equal to 0 and find critical values, because that's where we find minimums and maximums. So we know we need to take a derivative of this thing. I don't want to take a derivative of a product. I can, but I don't want to. It just makes the math uglier. So why not FOIL this out and then bring the x in? So let's FOIL it out. We get 9 minus 12x plus 4x squared, right? This squared plus this squared, there's your 4x squared, and then plus 2 times their product. So 3 times negative 2 is negative 6x, times 2 is negative 12x. All of this times x. So now my volume is going to be 4x cubed, right? Minus 12x squared plus 9x. Right? All I did was distribute the x and then write it in descending order so it looks more like a standard polynomial that we're used to. Okay, so this is my volume. If I want to maximize it, take its derivative, 12x squared minus 24x plus 9, set that equal to 0 and solve. Well, the first thing I would notice is everything is divisible by 3. Right? Now that might make it easier for me to factor, because I know this has to be a 3 and a 1, because that's the only way 3 factors. And since this is a positive, they have to have the same sign, so it's either plus and plus or minus and minus, and since this is a minus, I know they have to be minus and minus. Alright, so now 4 is either going to be a 4 and a 1 or a 2 and a 2. If it's 2, then we get 2 times 3 is 6, and 2 times 1, so that looks like that works. 2x and 2x. Double check it. This gives me a negative 2, and then these two give me a negative 6, which gives me a negative 8. Okay, so I have 2x minus 1 equals 0. 2x equals 1, x equals 1 half, or I have 2x minus 3 equals 0, 2x equals 3, x equals 3 halves, right? 1 and a half. Okay, so we seem to have two answers. Are they both correct? Right? Can we have two answers? Well, absolutely. We can mathematically, numerically have two answers, right? This derivative is a parabola, 12x squared. It's pointing up, so it obviously must be doing, something like this. And there's our two zeros at 1 half and at 3 halves. So mathematically we can get two answers. Conceptually, can we have two answers? Yeah, it's possible, but normally with optimization problems, you're going to be able to optimize it, and you should have one answer that works. So check them both for logic. Do they both make sense logically, right? If x equals a half, so if this is 1 half and this is 1 half, by this I mean these distances here and here, right? Because we're cutting off a square that's 1 half by 1 half. What's left in the middle? Well, that's 1, so doesn't that mean this is a distance of 2? And we end up getting a box that's 2 by 2 by a half, or 4 by a half, or a volume of 2. Alright, 3 halves. Let's do 3 halves in red. If this distance is 3 halves, and this distance is 3 halves, right? This is 1 and a half, 1 and a half. What's left for the middle? 0, right? Because 1 and a half and 1 and a half is 3. So now all of a sudden we get a volume that is 3 halves times 3 halves times, because if x is 3 halves, this measurement, then this measurement is 0. We get a volume of 0 times 0 times 3/2, and we don't even have a box, right? We've got nothing. We basically cut the thing into 4 pieces. We get a volume of 0. So this one, even though mathematically it works, it doesn't work in the context of the question. And our solution is cut a 1/2 foot, right, or 6-inch square out of each corner, and that will maximize the volume of the box. Okay, that's optimization.